Okay, let's go ahead and get started. It's 9:30. So here we are today. We are at lecture 13, and we're in lecture 4. We're about halfway through of lecture 4, so that should be good. Lecture 4, as far as the notes go, the notes are broken down into different lectures, which are associated really with chapters of your book. But this is lecture number 13, and what I want to bring to your attention is the homework was due today, or you could have turned it in, or you can turn it in on Tuesday and still get full credit. No, Sunday, sorry, Sunday, you get full credit. All right, if you turned it in today, then you got 5 extra points if you did the extra work to get it done. Another thing I want to bring up to your attention is in, let's see, 1, 2, 3 lectures, so almost 2 weeks, a little less than 2 weeks, about 10 days, there's the midterm exam in class. I sent an email to everybody letting you know that you can use your computer, so you don't have to print out your notes. You can bring your laptops, and you'll have an hour and 15 minutes to solve a problem or two, homework style problem in class. All right? And for the online students, you will also have to, I should have put some notes on that. For the online students, you'll have to have a computer with a camera, or somehow your Zoom camera should be pointed at your desk so I can see your hands, and maybe even have your microphones unmuted so we can hear your environment. So we just need to basically see your hands and your paper and your desk. We can talk about that though. I'll send an email when it comes time for that, or an announcement to the class. Okay, and the last thing I want to bring to your attention is, do not forget, on the 24th, we have class from 8 to 9:15, and it's across the hall here in Torque 1030, on that day only. All right? Okay, good. So be cognizant of these events. And let's get back into our material. So is there any questions from last time? All right, good. Yeah, so what are we talking about? We're talking about plane waves so far in unbounded media. We're going to be discussing the properties of these plane waves in media where they don't encounter any interfaces between differing media. So we learned last lecture how to write the form of a plane wave traveling along the coordinate axis, right? We looked at standing waves, group velocity, power densities, and phase velocities, wave impedance, and so forth, right? All of the goodies that describe plane waves and the properties of them. But now what we're going to do is we're going to look at all these same quantities, but for plane waves which are traveling oblique with respect to the coordinate system. So we have an XYZ coordinate system here. we have still two plane waves that we're going to describe. One which is traveling at an angle theta I with respect to the z-axis. Previously, we talked about plane waves which traveled along the z-axis, which meant all the vectors were coordinate aligned. E was in the x, and y was in the, or h was in the y, and it was traveling in the z direction, right? But now we have the k vector, or beta vector in this case, which is traveling obliquely with respect to the z-axis at some angle theta I. We have two cases. We're going to describe these plane waves, breaking them down into two modes, which are called TE to Y or TM to Y. TE to Y means that the electric field is transverse to the y-axis, which means it's in plane because the y-axis is in and out of the board, right? So the electric field for this configuration is in the plane of the board. If you look at the next case, we have TM to Y, which means the magnetic field is transverse to Y, which means that the electric field is in the direction of Y. So it's in and out of the board. So any arbitrary polarization could be partially in the board, partially out of the board, can be described as a superposition of these two cases. And that's why we study them in this way and break them down into TM to Y, TE to Y. All right. So let's start with TE to Y. Remember, I could have an electric field that's pointed sort of diagonally out of the board. So I could project that electric field onto the y-axis. That would be a TM to Y component. And I could project it into the plane of the board, and that would be a TE to Y component. So let's start with the case where we consider the components that are projected into the plane of the board. We have unbounded homogeneous media of permittivity epsilon and mu. We have the k vector traveling at some angle obliquely to the z-axis at angle theta I. All right? Okay, all we have to do is we have to write both the k vector and the electric field vector in this coordinate system, in this configuration. So the first thing we note is that E can be described as E plus plus E minus. In addition to the forward traveling wave, of course, we have a traveling wave which is traveling backward or in the opposite direction. Its k vector is in this direction, and its electric field is like that. Each of these, the forward traveling wave and the backward traveling wave, have to satisfy E cross H gives you the direction of propagation, right? So E is here, H is into the board in this case. My right hand points into the board. I rotate my fingers from in the plane of the board from E toward H, and I get the direction of propagation, right? Here, I rotate my fingers from E toward H, and I get the direction of propagation. So they both are correctly defined. All right. So first, let's describe E plus. All right. So first, we note that everything is in terms of this angle theta I. All right. That's the angle of the k vector traveling obliquely with respect to the z-axis, right? The angle of the k vector with respect to the z-axis. We identify that same angle appears here and appears here, right? So we describe the electric field. We have E naught, which is the magnitude of the electric field, multiplied by cosine of theta gives you the x hat component from this triangle, right? So from this triangle, which you can calculate is this x component here is equal to E plus times cosine of theta, right? And then the z component is negative E plus sine of theta, right? Why is it negative? Because it points in the negative z direction, right? Points along the negative z direction, that x or the z component. The x component is positive because it points along the positive x-axis. All right, good. So E naught plus, and then cosine theta I, x hat minus sine theta I, z hat. And then we have e to the plus or e to the minus j beta r, right? E to the minus j beta r is the general form for the phase term. All we have to do to calculate this is find what beta plus is, because r is always x hat plus y hat plus z hat. So if we find what beta is, make sure you always include the minus when you use this form. The direction of beta, the vector itself, will correct this minus sign or plus sign depending on which direction beta is pointing. So we have to find beta plus. Well, this angle's theta I, so beta z, so beta plus is equal to, let's see, it has an x hat component, which is positive, right? It has an x hat component, which is, sine, right? Sine of theta I x hat, and then it has the magnitude of the beta vector. Plus, it has cosine of theta, beta, cosine of theta in the z direction, right? From trigonometry. Good. All right. That's the hardest part to solve these, right? You have to find the electric field vector and the beta vector. And all you have to do is find the right triangles, determine the angle, and then you can easily use trigonometry to find the components.
I have a question. Why the angle of propagation is equal to the angle between the electric field?
Yeah, that's an excellent question. And that's the whole difficulty in solving this problem, is finding that angle, right? That angle theta I will be an angle in the electric field the decomposition as well. The way I like to visualize it is if you grab the tip of the v plus vector, or the beta vector, and you move that k vector down to the z-axis, closing this angle theta I. If you do that and you follow which angle closes in the triangle of the electric field, then you can identify which angle is theta I in the electric field decomposition. Yeah? So you can imagine if I take this point and I bring it down this way till it aligns with the z-axis, this angle is going to close, right? But at the same rate, will this angle close or will this angle close? Because this vector here has to stay orthogonal to this vector, right? So at the end, that vector is going to be vertical, right? So it's this angle that closes. This one becomes 90 degrees, right? So once you know which angle in here is theta I you know from the k vector. Once you know which angle theta I is in this triangle, then you can easily decompose it into its components, yeah? Good. Very nice. All right. So you find beta plus, you find beta minus, you know R, you can write down the electric field. So here's the electric field then. This vector has E plus and E minus, right? Good. And then H you can find easily once you have E, because you can use the right-hand rule to find the direction, and then you can divide by eta to get the magnitude. But we know that the magnetic field in this case points in the y direction because we're talking about E to Y modes, right? We already know it's in the y direction. We just have to divide the magnitudes here by eta, and we have to note that we have to take care of the right-hand rule. So the direction of this one is minus, the negative, and the positive one is positive, yeah? Okay, good. You'll get a lot of practice of this. Same thing for Tm to Y. Now what we're going to consider is the case where the magnetic field is in plane and the electric field is in and out of the board. So we have to do the same thing. We have theta I here. We need to identify which one of these angles is theta I. And the way that I like to do it is, by the tip of that vector, you pull it down to the z-axis. Which angle is going to close? It's going to be this angle that closes, right? At the same rate as this angle. Or you can probably just use, regular trigonometry. There's probably a way to geometrically find that angle in a more systematic way. But, qualitatively, you can just try to see when you close this angle, which one of these angles changes at the same rate and is the same angle. Okay, good. So we have the same situation. We have a positive traveling wave, a negative traveling wave. Now we have the magnetic field in plane. So the magnetic field needs to be decomposed into an HZ component and an HX component. And then the negative traveling magnetic wave or magnetic field, we have HX and an HZ component, right? Okay, so do the same thing. You find beta, and then you can write down the electric field. Now we know the electric field is in the Y direction. In both these cases, it's in the positive Y direction. And the magnetic field you can find by dividing, or the magnetic field you can find directly, right? We calculate, or no, okay, so what it looks like is we're finding the electric field first. The electric field is easy to find. It's in the Y direction, right? We know it's in the Y direction as e to the minus j beta plus and minus R. Plus R. Oh, this should be a minus R. So make that change, yeah? This should be e to the minus j minus R. Okay, and then you can write down the electric field, then you can use the rules to find the magnetic field. It's probably faster to do it like that, right?
What's the relation between The v vector and the beta vector.
They're the same, right? So what they're introducing here at this point in the book is that there's a direction of propagation. They're calling it v, to denote that sort of that has phase velocity in that direction. And there's a plus superscript denoting that that's the forward traveling wave. We have the minus traveling wave with the v minus. But what you'll learn to think of it in terms of k or beta. So E cross H gives you k in direction. All right. Good. Okay, now we need to define what's called the directional wave impedance. So the wave impedance now, since everything's not coordinates aligned and axis aligned, can have multiple definitions, right? So other directional impedances toward the X and Z directions can also be defined, all right? These impedances are obtained by dividing the electric field component by the corresponding orthogonal magnetic field component, all right? So it's still gonna be a coordinate aligned quantity, the Z component of E divided by the Y component of H, right? Before it was all of E divided by all of H because E and H were aligned with these axes, right? But now it's gonna be partial E or partial H. One of them will be full, depending on if it's TE to Y or TM to Y, because one of them is axis aligned, the one that's orthogonal to the board. But the other one's gonna only have part of that component, right? Because we're talking about only the Z part. So let's see, TE to Y modes. This one is TE to Y, right? So we're talking about part of E, only the Z component of E, and all of H, because H is in and out of the board, right? H is in the Y direction. So ZX, the wave impedance along the X axis, right? The wave impedance with respect to the X axis for the forward traveling wave is minus EZ over HY. EZ, we know from the last slide, had a sine theta multiplied by it, right? Minus sine theta. Let's see, TE to Y. Here. That's the Z component of E in the TE to Y, yeah? Minus sine theta times E naught plus. So we have a minus sine theta times E naught plus. Now, why is it minus EZ over HY? Because you want the components, so these two components are chosen such that the cross product of the electric field and the magnetic field, so E cross H, are chosen such that they correspond to the direction of power flow, is in the direction of wave travel. So E, so here for the plus traveling wave, ZX plus, we want E cross H to give us the direction of propagation, right? So we need to choose those components. Now E, H is in the Y direction. So if we have, look, EZ, so EZ, we're doing EZ over HY, right? EZ is in the negative Z direction. So if we took EZ like that, and we crossed it with HY, so like that, I guess how would you do that? It has to be in the direction of wave travel. So we have to negate it, right? We have to negate EZ so that we can have EZ like that, cross with HY gives us a component in the direction of travel, right? Direction of travel, the direction of wave travel is in the direction of wave travel, right? So the wave travels in this direction. So you can't take EZ crossed with H and get the direction of travel, right? What you do is you take the component of E in that direction, and so you take it in this direction. You want to look along the Z axis, right? So we have EZ in that direction. If we take EZ in this direction, then we cross it with HY. Like, how am I doing this? So I gotta think about this. EZ in that direction, crossed with HY. It has to be in the plane of the board, okay. And then you cross it with HY. Let's see, that's kind of confusing, right? Because ZX, oh, not Z, we're talking about ZX. This one is ZX, all right? So we want to look in the X direction. Now it makes sense. All right, so what you want is EX or EZ crossed with the HY to give you an X direction of travel, right? So EZ crossed with, so where's the Z? Z's like that. You cross it with Y. Okay, good. So here's Z, right? If you take Z and you crossed it with y. So take your hand, turn it to the z-axis, cross with y. That gives you the negative x direction, right? Which is incorrect because the direction of travel has a positive x and a positive z. So you need to negate it. Right? Or you can think of it as this z component is in the negative z direction, and we want to cross that with y, and that gives you the x direction, right? Okay, yeah? All right, you just have to sit and think about it. All right, so zx plus minus ez over hy, you get eta sine theta because e over h is eta. So think of it like this. We have zx plus minus ez plus divided by hy plus, well, minus ez is minus into minus sine of theta times e, right? Let's say e naught plus, and then you divide that by hy plus, which is all of h. So that's h naught plus, I guess you can say. So e over h is eta, so this becomes eta sine of theta I. Yeah? All right. That's also equal to ez over hy for the minus direction, or the minus direction of travel. So now we can do the other case, which is the zz plus, right? So this is ex over hy. So if you take ex and you cross it with hy, that gives you z, right? That one's a lot easier to see. So this one right here, ex over hy should give you z, right? So ex plus is in the x direction, hy is in the plus y direction. So you do the cross product, ex cross with hy, that gives you z. And the component, the wave is traveling partially in the z direction. So that's the correct combination. You get eta cosine theta I because the x component was cosine of theta, right? And then you get zz minus, if you're looking in this direction now, it's negative. And you can define the same thing for the tm to y modes. All right? These are useful when you develop transmission line models for obliquely traveling plane waves, where you want to calculate maybe the reflection from a infinite half space of different permittivity. You can model it as a transmission line problem, and if it's traveling obliquely, then you can use these wave impedances for TE and TM modes, TE and TM modes, in order to complete the model for that, for the oblique incidence. It makes the problem much easier. All right, phase and group velocities. So we can also define the phase and the group velocities for waves that are traveling obliquely with respect to the coordinate system. So phase and group velocity and direction of wave travel for TEM modes, remember these are plane waves, which are TEM, was shown to be, for TEM modes, is shown to be the phase velocity is equal to the energy or the group velocity, which is equal to V, which is equal to 1 over the square root of mu epsilon, right, in the medium. All right, the velocity of the plane wave along the z-axis is represented by the velocity of this red dot. So remember, what is the phase velocity? What is the definition of the phase velocity? We follow a point of constant phase on the wavefront as it moves, right? And we track the velocity of that constant phase point. So this point, here's the wavefronts, right? These are the constant phase planes, these dashed lines. So the wave is traveling along this direction, and the constant phase planes, it's a plane wave, are orthogonal to the direction of travel. They have constant phase in those planes, right? A point of constant phase is this point, right? The phase velocity for the plane wave itself, that's not a directional quantity, is the velocity of this point in this direction, right? That's V, which we defined here. But what about the velocity of this point on the wave as it travels along the Z direction? It's going to be some projection of that, right? We call that the directional wave, or not the directional wave impedance. You call that the velocity along the z-axis. The phase velocity of the plane wave along the z-axis is represented by the velocity of this red dot, right? So if you follow this point along the z-axis, then what you will see is that it's v, this vector. I can define a vector v, which has components along the z and the x-axis, and that represents the magnitude of that vector is the velocity of the plane wave, the TEM mode, right? Then I can resolve that vector into its z and x components, and I can get the phase velocity along the z-axis. So you can see that z component is v by cosine theta, and the z component is v times cosine of theta. Oh wait, sorry, hold on. Okay, so we have two velocities here, right? We have the energy velocity here, and we have the phase velocity. So this point here is on that wavefront, and it's going to travel along this axis. That phase velocity is v divided by cosine of theta. All right, which is greater than the phase velocity of the plane wave in the direction of travel. And the energy velocity, the group velocity, is v times cosine of theta, which is this component of the velocity vector. Both the velocities must satisfy this equation. So you can get this result from this one. Remember this equation, this result always holds. Okay. We can also calculate power energy densities in particular directions. So we can have power and energy density in the R direction, which is in the direction of travel. That's nothing but 1/2 real part of E cross H conjugate, right? We learned that in lecture 1, which is 1/2 real part of. Now we can write down what E is and H is in the oblique traveling plane wave. And we can solve this cross product. And what we get here is the expected result, which is this. Which is magnitude E squared over 2 eta for a plane wave, right? But that is composed of an X component and a Z component. The X component is this sine of theta times that quantity. So part of this travels along the x-axis. Part of this is directed along the x-axis, I suppose. And part of this is directed along the z-axis, right? So you can define how much power is flowing along the z direction and how much power is flowing along the x direction. Okay. All right, good. So those are just ways to describe the different properties of plane waves in TEM or plane waves that are traveling at angles with respect to the coordinate system. Now we're going to study what happens when we have plane waves traveling in lossy media. So the wave equation that we have here is this one, right? We've already solved the case where sigma was equal to 0 for lossless media, which was del squared E plus omega squared mu epsilon E, which is nothing but k squared E, is equal to 0. But now we have this additional term, right? If you go back to lecture 3, the beginning, we derived the wave equation assuming that sigma was not 0, and then we specialized it to the case when sigma was 0. All right, for lossless media. If the medium has a sigma, then we have to solve the wave equation in this form, right? And we define gamma squared as j omega mu sigma minus omega squared mu epsilon. And we solve this wave equation. Then we can write this wave equation like this. And when we do that, we can break this into 3 identical wave equations in rectangular coordinates only, as we know. And we can separate the gamma, the complex propagation constant, into its real and imaginary parts. And we call the real part the attenuation constant and the imaginary part the phase constant. We've seen this already, right? Okay. Now, assuming a uniform plane wave with the electric field pointed in the x direction, so it's polarized in the x direction, we're going to talk about polarization. But the electric field's in the x direction and it's traveling along the z-axis, we have to solve this wave equation, right? Why? Because we're talking about only the x component. The electric field only has an x component, right? Of course, we could solve any of the 3 and we'd have the solution for either because they're all the same differential equation. But we're going to solve this one. Del squared dx minus gamma squared dx equal to 0. We know that the solution to this differential equation has only h of z because it's traveling only along the z-axis and it's a plane wave. Therefore, the electric field does not vary with respect to y and x by definition of a plane wave. So we have only h of z. The solution to that is E naught e to the minus gamma z, E naught e to the plus gamma z, right? And we can separate gamma into its real and imaginary parts. And what we have here is a plane wave now. This is familiar, right? This part, E naught e to the minus j beta z. That's nothing but a plane wave traveling along the z-axis, right? But now we have this real exponential. It doesn't have a j in it. It's e to the minus alpha z, which is nothing but the normal exponential function that decays, right? e to the minus alpha z. All right. So what happens to our plane wave? Well, we have, if we take the real part, multiply by e to the j omega t and take the real part, we can plot it along the z-axis. And what do we get? We get cosine of beta z, right? And then e to the minus alpha z. And then the amplitude the initial amplitude is e naught plus. So we start here at e naught plus when z is equal to 0. And z is equal to 0 here gives us e to the 1, which is, or e to the 0, which is 1. And the cosine function does its oscillation thing, but then e to the minus alpha z damps that oscillation, right? So it's a lossy medium. As the plane wave travels in the medium, energy is being converted into heat through the sigma of the medium, and therefore the plane wave amplitude is decaying with respect to the z direction. So here's the wavelength, which is beta over 2 pi, right? Because beta is 2 pi over lambda. And we can define this quantity here. If we start with an initial value of e naught plus, then at some point along the z-axis, the amplitude will decrease to 1 over e of that value, e to the minus 1 of that value. All right? So e naught plus times e to the minus 1 is this point here. All right? At the z at which that happens is called the skin depth. And it's also equal to 1 over the attenuation constant in this case. Why is that important? Because I don't know if you remember from your circuit theory, there's a definition of something called a time constant, right? And what you can do is when you want to describe the dynamic behavior of a circuit, you can tell somebody what the time constant is, and then they automatically get a feel of how fast the decay is, right? Because 5 time constants, we know that the signal's pretty much gone. 1 time constant is 1 over e. 2 time constants is, so this is 37%, 1 over e, right? And then at 1 over, or 2 time constants, I can't remember, it's some, 60%, or I can't remember exactly. It's e to the minus 2 is what it is, right? But anyway, if you tell somebody the skin depth, then they can get a feel for how the field decays in the medium, right? If you tell somebody the time constant of an RC circuit, they can get a feeling of how fast the energy decays in that circuit, right? Okay, so let's dig into this a little bit more. We have gamma squared, which is the complex propagation constant, j omega mu sigma minus omega squared mu epsilon. Let's break it into its real and imaginary parts, right? Okay, so we say that gamma has a real and imaginary part, alpha and beta. And if we square this gamma, then we get alpha squared plus 2j beta alpha minus beta squared, right? So now we can compare this right-hand side to that one up there. And we can start identifying the various terms, right? So this is our gamma, right? We defined it as having a real and imaginary part. We square this definition, we get this. Then we set that equal to our definition of gamma that we got from deriving the wave equation from Maxwell's equations, right? So we get this equality. We have this equality here. From there, you can start matching up real and imaginary parts on the right and left-hand side. And what you get is, this is the real part, alpha squared plus 2, or no. You have this on the left side, you have this on the right side. So all I did was copy it there, right? The real part is alpha, there's beta squared here, and there's omega squared mu epsilon, right? So these are all the real parts. The imaginary part is, we have a 2 alpha beta, and we have an omega mu sigma. 2 alpha beta, omega mu sigma. All right, so, okay, now we have a system of 2 equations and 2 unknowns, right? We want to find alpha and beta in terms of sigma, omega, mu, and epsilon. So what we've done is we've separated this into real and imaginary parts. We have 2 equations now. There are 2 unknowns, alpha and beta. We assume we know mu, epsilon, and omega. So now we can solve this system of 2 equations and 2 unknowns for this, alpha and this beta. These are the general forms of what alpha and beta are, given sigma of the medium, given the frequency omega, given the permittivity epsilon, and the permeability mu of the medium. All right? We're going to specialize this to various cases, but this is alpha and beta. Good. Okay. So the units of alpha are in Neppers per meter, right? So I just put a little note down here. What is a Nepper per meter, or and how do you convert it, right? What is a Nepper per meter? We know what a dB is, right? It's a ratio of powers, and you take the logarithm of that, right? So a Nepper is the same thing, but it's the ratio of field amplitudes. Because we're talking about e to the minus 1, with e naught plus divided by e to the minus 1, right? So we're talking about ratios of field amplitudes in sort of a logarithmic or exponential scale. So Neppers is equal to the natural log of the magnitude of E at 0.1 divided by the magnitude of E at 0.2. Similar to how a dB is the log of P1 over P2. How do you convert from Neppers per meter to decibels per meter? Well, we have a dB is 20 log of this field amplitude E to the minus alpha Z, right? So we're going to say this E to the minus alpha Z at some point with respect to its maximum, which we're saying is 1. All right. So we bring down the minus and the alpha and the Z, and we get minus 20 alpha Z log of E, which is minus 20 alpha Z log of E is 0.434. And then we have this conversion factor, which is a dB is equal to minus 8.68 of a Nepper. So alpha in Neppers is 1 over 8.68 times alpha in dB. All right, so that's a handy factor that you could use in your homeworks if you come across problems that involve these, right?
Can we find alpha and beta mathematically, on paper, or do we require software solution?
No, you can. This is it right here, right? So once you know the medium properties, so say I have a plane wave, we'll probably do an example, but we have a plane wave traveling in seawater, for example, right? And we know the sigma, the loss of seawater. We know the permittivity of seawater, like 81, and we know the permeability, right? So once you know mu, sigma, and epsilon for the medium, you can calculate alpha directly right here.
But that equation, coming to the conclusion that alpha is equal to that part, is something that we can derive on paper, or do we require software to get that?
No, we just did that, right? So we derived it on paper. So we started from the wave equation, which is derived from Maxwell's equations. We solved the wave equation. We solved this one for assuming complex gamma. So this is a complex number now, right? And we ended up with these solutions here that have that. From there, we were able to, we can take the gamma squared, which we know from Maxwell's equations we got here, right? We defined that, which is part of this term, part of that term, right? We take the gamma squared, and we know that gamma squared should be separated into real and imaginary parts. And we did that here. We said gamma squared is this from Maxwell's equations. Gamma should have a real and imaginary part. Let's square that definition, and we get this. Then we set it equal to gamma squared that we got from Maxwell's equations, right? And then from there, we can separate, from here, we can separate into the real and imaginary part. So it was an analytic solution, right? An analytic process. We wrote it on paper. Yeah, definitely. If you have sigma, epsilon, mu, and omega, you can calculate alpha directly. Okay. Okay, so we know that the wave impedance is E cross H, right? E over H, or E over H rather. The wave impedance is E over H. But when there's loss involved, then we get a complex wave impedance, right? So let's derive that and take a look at that. We have EX here. We solved the wave equation. We got EX here, which is HZ, and we had this solution, right? From there, we can calculate the associated magnetic field using Faraday's law. If we use Faraday's law, plug in this E and solve it, then after all of the algebra here, you get to this point. Y hat, magnetic field is in the Y direction, and we have E naught plus E to the minus gamma Z minus E naught minus E to the gamma Z, and then we have this factor in front, right? Remember how we defined the wave impedance before? We solved the wave equation. We did the exact thing we did on the top of this slide, but for a lossless medium. And we didn't have these terms then, right? The alphas. We didn't have those. And then we used Faraday's law to calculate the magnetic field from our solution of the electric field from the wave equation. And then we noticed a factor out front, which was 1 over the square root of mu epsilon, right? Mu over epsilon. So we did the same exact thing here, but now starting with the assumption that the medium has loss, so there is an alpha, and we got this wave impedance out front. If we ratio these two now, then we get a complex number. This is a complex number. The complex wave impedance is also the intrinsic impedance of the medium since the wave is TEM. Okay, but this is the wave impedance here. The square root of j omega mu over sigma plus j omega epsilon. And we denote it with the subscript C, meaning that it's a complex wave impedance. Whenever this is a complex number, you know the medium is lossy, right? We can specialize this to the case of no loss, right? What happens then? Sigma is equal to 0 in the lossless medium. J omegas cancel. We get the square root of mu over epsilon, which is what we got in the lossless case, right? So the effect of sigma is to make the wave impedance complex. All right. So when sigma is 0, we get the wave impedance of lossless media. When sigma is not 0, what is the effect of having a complex ratio between E and H? That means that it will introduce, the loss will introduce a phase shift between E and H, right? E over H is a complex number. So that means not only is the magnitude a particular ratio, but there's also there's a phase difference between the two field components, right? And whenever we see a phase difference between E and H, that tells us that there's loss, right? There's some kind of decay. So when sigma is not 0, E and H are no longer in phase. In the lossless medium, E and H are in phase. Remember the pictures we drew of plane waves like this for vacuum. E and H are always in phase, right? They both go to 0 at the same point. They both have their maxima at the same point. They go back to 0 at the same point. They go to their negative maxima at the same point, right? They oscillate in phase, all right? So this is a vacuum. And then in a dielectric medium, what is the difference between this medium and a dielectric medium? What do you think? What did we derive a couple of slides ago, last lecture? We said, what about the phase velocity in a dielectric medium? Slower, right? So this wave moves slower than this one. I don't know if the animation is good there. Okay, it moves slower, right? Anyhow, what else? We know that the wavelength is shorter, right? It's a consequence of it being slower. Yeah? So in a dielectric medium, we know that the wavelength is much shorter. As a matter of fact, the wavelength in the dielectric medium is lambda, say D, is lambda naught divided by the square root of epsilon r, if it's not magnetic. All right? And this one you can easily get from the beta, right? So let me derive it for you real quick. So if you say beta in the medium is omega square root of mu epsilon. Okay, well that's omega times the square root of mu naught epsilon naught times the square root of epsilon r, right? Or beta naught times the square root of epsilon r. All right, then what you can say is that the left-hand side we could say is 2 pi divided by lambda d, and the right-hand side is 2 pi divided by lambda naught times the square root of epsilon r. And then from there, you can cancel the 2 pi's, and you can solve for lambda d is lambda naught over square root of epsilon r. All right? What does that say? That says that the wavelength is reduced from what it is in free space by the square root of epsilon r. So if epsilon r is, let's say, a 9, then the wavelength in the dielectric will be 1/3 of what it is in free space. Yeah? So we can see the wavelength is shorter. What else do we notice about these two plots? What do you notice is the difference? The what? Very good. So remember, in what defines the ratio of E over H, the wave impedance? It was directly a function of the medium properties, right? E over H is the square root of mu over epsilon. So in free space, we have E over H with the small h and a large e, right? 377 ohms is the ratio, the wave impedance in free space. So the electric field should be 377 times longer than the magnetic field. In the dielectric now, though, E over H is not 377. It's 377 divided by the square root of epsilon r. If epsilon r was 9, then it's a third of that, right? So this is the electric and magnetic field are more equal in magnitude than they are with respect to than they are in free space, right?
Actually, the electric field is lower than in the vacuum fields, right? Because I don't know if it is the H which is larger or the electric field which is lower.
Yeah, that's okay. So that's a very good observation. But what we've done here is we've plotted these, assuming that the electric fields are the same. So the magnetic field is going to change with respect to the wave impedance, or else comparing these two plots wouldn't make sense, right? But it's true, if they were not normalized together like that, then it could be that the electric field reduced and the magnetic field stayed the same, right? But that's not the case. To make a comparison, we assume the electric fields are the same, and the wave impedance of the medium is much higher here, right? Or lower rather. And wait, square root of mu over epsilon, right? So if epsilon increases, yeah, it's lower here, yeah? So then the magnetic field is greater with respect to vacuum. Okay. This plot over here now, what's happening here? So this is a lossy dielectric. By the way, I got these from a really, really cool professor named Raymond Rumpf from University of Texas, El Paso. If you are interested in electromagnetic theory, I implore you to go to his website and look up some of his materials. He has very good materials for further study. But anyway, here, this is a lossy dielectric, right? So a lossy dielectric here, we have the same situation as here, except now we have e to the minus alpha z, right? Yeah? It decays. What else do we expect in this plot? Probably hard to see. Remember what I said over here. Wave impedance here is complex. Here it's real. Here it's a complex wave impedance, which means that E and H are no longer in phase. So we expect E and H to still be in phase here. Here's a 0 point. They're both maximum at the same time, right? But here, look at this. There's a maximum here, and it's not the same maximum there. They're not in phase anymore. They enter the medium in phase, but they fall out of phase. I don't know if they enter in phase, but anyhow, they are out of phase at some point here, right? There's a phase shift between E and H because the wave impedance is complex. So the wave impedance reduces the amplitude and adds a phase shift because that the ratio of E over H is now a complex number. All right, good. Okay, let's look at power density and skin depth. So the power density of a TEM wave in a lossy medium. So now we can calculate the power density in the lossy medium. Still 1/2 real part of E cross H conjugate. But we had the E to the minus alpha z's now, right? So, and we have our wave impedance here, which is complex. So we're writing E as E to the minus alpha z, E to the minus j beta zx, right? TM mode in a lossy medium, axis aligned. Now we're going to find the magnetic field from the electric field by doing the right-hand rule to find its direction and dividing by the complex wave impedance now, instead of just the real wave impedance, right? So A to C. Now that this is a complex number and we conjugate 8 when we find the power density, we have to also conjugate that in wave impedance. So don't forget to do that. So if you do all that, then you end up with the same result we had before for lossless media, but you have this additional term now, which is E to the minus 2 alpha z, because we're talking about power, and the real part of 1 over A to C conjugate. All right. Why is it the real part? Because we took the real part here, right? To find the power density, real power flow. So what does that mean? The power is decreasing with Z, right? We expect that. So here's a plot of that. We have EX at some distance Z divided by EX at 0 at the origin, right? So EX at 0 divided by EX at 0 is 1, right? So we normalize it with respect to the power at the origin, EX at 0. And the power decays with respect to, or no, this is the field, right? Field is E to the minus alpha Z. So the field is decaying like this. We know the skin depth is when, at what Z distance does the field decay to E to the minus 1, or 1 time constant, 1 skin depth. And we already defined the skin depth, right? It's E to the minus 1. So 36.8% of it's a value at the entrance of the medium. And we can define that as 1 over alpha, right? which is, and here's alpha in the denominators that we derived a slide ago. Okay, good. Any questions? Very nice. Yeah, these are just properties of the plane waves traveling. We'll get to some fun scattering and multiple interface problems soon. Okay, so now let's specialize that alpha and beta to different kinds of media. There are good dielectrics, good conductors, and then there's something in between, right? So let's look at Ampere's law, curl of H. We have J conduction current. We have J displacement current, right? The conduction current is sigma times E. The displacement current is J omega epsilon E, right? And we can factor out the E, we get sigma plus J omega epsilon. If we ratio sigma to omega epsilon, so this sigma represents a conductive current, omega epsilon represents the displacement current, right? The displacement current is the so the displacement current in a dielectric medium, right, is the kind of, it's not really a flow, but it's the oscillation of the bound charges, right? The polarization. And the conduction current is associated with the loss in the medium and the charges that are free to move. Okay. Okay, but remember, sigma also incorporates epsilon double prime in this case. So there's also some loss in the dielectric. All right. We take the ratio of sigma over omega epsilon and square it. And if that's much less than 1, then what does that mean? That means that omega epsilon is much greater than sigma, right? Which means the displacement current dominates. So we can call that a good dielectric. All right. So since sigma over omega, why do we form sigma over omega epsilon? Why not just j omega epsilon over, or sigma over j omega epsilon? Because if you go back to your alpha and beta, that term is there, right? So we want to look at that term. And the reason why is because we can use a binomial expansion to underneath the square root term to simplify this, right? For good dielectric cases. So at alpha, omega squared of mu epsilon, this is the exact equation for alpha in general. This is the form that works for all cases. Now, we've said that sigma over omega epsilon squared is much less than 1. If it's much less than 1, we can use a binomial expansion to represent that square root. And we have this 1 plus 1/2 sigma over omega epsilon squared minus 1/8 sigma over omega epsilon to the 4th power and so forth. If we keep only the first 2 terms, because this is much less than 1, then this is the result for alpha. For a good dielectric, alpha is omega squared of mu over epsilon, or excuse me, omega squared of mu epsilon 1/4 square root of 1/4 sigma over omega epsilon squared. All right. All right. So these are cases that you can apply in your research when you identify that the dielectric is lossy, but it's not very lossy. Then you can approximate your alpha and your beta in this way. So beta then becomes, using the same thing but keeping only the first term, omega over this omega squared of mu epsilon, which is that of free space. Let's look at what happens to the complex wave impedance. If we do the same thing now, we have j omega mu over sigma plus j omega epsilon. What we're going to do is divide everything by j omega epsilon. So this becomes 1. This becomes sigma over j omega epsilon. This becomes j omega mu over j omega epsilon. And if you take the, this becomes the square root of mu over epsilon, right? Let's see, how does that happen? J omega mu, j omega epsilon. Okay. Oh, that's right. So omega epsilon is very large, right? So this term goes away. Sigma over omega epsilon is much less than 1. So omega epsilon is much greater than sigma. Here we have sigma over j omega epsilon. We know sigma over omega epsilon is much less than 1, so we can ignore that term. And then the skin depth becomes this. All right. We're going to put all this in a table at the end, so you can just use the table. Now the converse is when sigma over omega epsilon squared is much greater than 1. When it's much greater than 1, that means sigma dominates. And when sigma dominates, the medium is very lossy. We call that a good conductor. All right. You can use the same binomial expansion. If you go through the process now, keeping the first term, we get alpha is the square root of omega mu sigma over 2. This is a common formula you'll see a lot for good conductors. This is the attenuation constant in a medium which is dominated by loss. And also like metal, lossy metal, for example, beta comes out to be the same thing, right? The square root of mu omega sigma over 2. And therefore, or not therefore, but another consequence, the wave impedance becomes the square root of omega mu over 2 sigma 1 plus j. And the skin depth is the square root of 2 over omega mu sigma, because we know skin depth is 1 over alpha, and alpha is this. But the one thing to notice is that beta and alpha are equal in a very lossy medium. All right. So we put this in a table now, and we have all the expressions for TEM modes in lossy media. The attenuation constant, the phase constant, the wave impedance, which is complex, the wavelength, the velocity, and the skin depth. All right. These are the general forms, the exact forms for alpha and beta, and for the wave impedance, and for the wavelength, velocity, and skin depth. Right. Then we specialize it to the good dielectric and the good conductor cases, and we got these approximate formulas here, right? Okay, so all you need to do is come to this table when you need to use these formulas. All right, you've probably seen this stuff before, to be honest, in your last electromagnetics course. All right, okay, so gosh, so now we got to do the oblique case in lossy media, right? This is the most complex case. But I think that's almost the last thing we're going to look at. Okay, so what did we do to handle oblique plane waves in the lossless case? We wrote the beta vector, right? So we had to resolve our electric field and our magnetic field in the TE to Y, TM to Y case in terms of its two components along the axis. But then we also had to define the beta vector. We're going to do the same thing here, except now we're going to define the gamma vector, right? Gamma plus and gamma minus. The electric field will still have the same decomposition. So the only difference in this case is we need to find what the gamma plus is and the gamma minus, all right? Okay, so gamma plus and gamma minus are exactly the same as they were in the lossless case in terms of its resolution, in terms of components or decomposition, in terms of X and Z components. We had beta out front before, but now we're gonna have gamma, right? And gamma is alpha plus J beta. So what's gonna happen is we're gonna end up with, so if we take that and plug it back into the electric field, E naught, this is the same as the lossless case. Now we have e to the minus alpha plus J beta. This term is the same as the lossless case, right? And we have the same thing for the minus traveling wave. And the magnetic field is the same, except now we have a complex propagation constant and the complex wave impedance, right? Okay, so it's identical. It's the same thing, except we replace complex wave impedance and complex propagation constants. All right. Because the wave is a uniform plane wave in the direction of travel, the wave impedance in the direction of travel is the intrinsic impedance in the medium, which is complex. We can also have the directional wave impedances the same as the lossless case, except the wave impedances are now complex. So repeat the results, except now this is A to C, right? All right, good. So that wasn't too painful. Power and energy densities. Okay, so you could do the exact same thing, right? It's the same thing as the lossless case, except now we have e to the minus 2 alpha. We have an alpha here. And then we have the real part of the 1 over A to C. Same thing we had in the lossy medium case, but not oblique. And we end up with a very similar formula, right? So you can go through these. These are exactly the same, except we have complex wave impedance now. Or sorry, we have obliquely traveling plane waves. All right, done with all of that. Properties of plane waves traveling in lossy and lossless media. Now we're going to talk more about the polarization of an electric field, an electromagnetic wave, right? So polarization, there are three main types of polarization, right? There is linear polarization, the circular polarization, and elliptical polarization. Elliptical is the most general case. And what is polarization? Polarization is defined as the locus traced out in space by the tip of the electric field. So let's define a little more formally. The polarization of a uniform plane wave describes the locus, sort of the path, traced by the tip of the E field vector. So it's the E field vector that defines a polarization. and it's in the plane orthogonal to the direction of propagation at a given point in space as a function of time. That's everything. That's the definition. So if we can understand this sentence here, then we'll be good, right? So let's look at this. For the plane wave, we look at a plane. The plane wave is traveling in the z direction, right? We look at a plane orthogonal, in the plane orthogonal to the direction of propagation. We look at a plane orthogonal to the z, or the direction of propagation, which is the xy plane. All right? Then we calculate the locus of the tip of the electric field vector in that plane as a function of time. The locus is the curve in that plane, right? So the electric field vector as a function of time in this plane at this point is forming a linear line, right? So that is linear polarization. We do the same thing with the circularly polarized wave, circularly polarized plane wave. We look in the xy plane in the direction orthogonal to the direction of propagation, and we follow the tip of the electric field vector as it goes through that plane, yeah? And we trace out a curve or the locus, and it's a circle. So that means that that's a circularly polarized plane wave. And we'll dig into circular polarization, all that. This is really cool. And then if it traces an ellipse, it's an elliptical polarized plane wave, right? All right. Let's look at a linearly polarized plane wave. Let us consider a harmonic plane wave with x and y electric field components traveling in the positive z direction, which is into the page. All right. So this is the graph here. These are scripties, right? Meaning that they are a function of time. To find the polarization, we have to find the locus as a function of time. So to consider the instantaneous forms of the electric field, right? The wave is traveling into the board, into the z direction, into the board, right? So that's why x is vertical and y is horizontal, because x cross y always gives you z in a right-handed orthogonal coordinate system. All right. So let's say the electric field in general can have an x and a y component, and we can represent this time-dependent or instantaneous electric field in terms of the real part of the complex or the time harmonic electromagnetic field multiplied by e to the j omega t, right? So the electromagnetic, the plane wave is ex plus the complex plane wave, time harmonic plane wave, ex plus e to the minus j beta z. Then we multiply by e to the j omega t. Take the real part, we get the time-dependent one, right? Okay, so this is the most general case. The electric field could have an x and a y component for a plane wave, which is traveling along the z-axis, right? In this case, into the board. All right. We can then take the real part of these expressions, and we get ex naught plus is cosine of omega t minus beta z plus some phase delay. Where did this phase delay come from? So remember, this amplitude is complex in time harmonic, right? It's a complex number. Here I've said ex naught plus, which is the amplitude and magnitude of that complex number. And then I put the phase, I've separated this into its polar form. So it has the magnitude and the phase. I've incorporated the exponential. All right. So remember, these are complex coefficients in the time harmonic case. All right. And then we have E naught y, so the y component, and a phase shift in the y direction. In the plane z equals to 0. So to make life easier, we always observe these or try to describe the polarization in a plane where z is equal to 0. It makes it easier because the z dependent terms go away, right? In the plane at z equal to 0, you can trace the polarization of a plane wave in any plane orthogonal to the direction of propagation. So let's choose that orthogonal plane to be the one at z equal to 0. So then this term goes to 0, that term goes to 0, and we have a couple of cases we can assume. So in the plane z equal to 0, that goes away, that goes away. If we assume ey naught plus is equal to 0, then this is the electric field. Because the y component, this is set equal to 0, right? Okay, well, that means we get this figure to the right, right? So it's a straight line. We can see the electric field vector here plotted at different times, and then it goes negative, right? It's in the x direction only. There's no y direction for this case. And it's E naught x e to the cosine or cosine omega t plus phi, right? So the electric field, here's the electric field as a function of time. right? We need to trace that electric field as a function of time in the plane orthogonal to the direction of propagation. Here, we can make a table, t equal to 0, t equal to pi over 2, t equal to pi, t equal to 3 pi over 2, t equal to 2 pi, right? And we can, or omega t equal to that. And no matter what time we choose, we can make a table of a bunch of different times to calculate what the electric field is doing as a function of time. It's always in the x direction, right? So the locus is a vertical line along the x-axis, right? This is the locus here. So that means that it's a linearly polarized plane wave. So remember here, this is what it looks like. These planes go off to infinity in both directions. The electric field has its strength, the strongest magnitude here, then it gets weak to 0, then it's strongest here, then it goes to 0 again, right? All right, so in this case, the field is said to be linearly polarized in the x direction. Right. So this figure up here shows the electric field oscillating, but it also shows the magnetic field, the orthogonal component oscillating. Okay, now let's look at the other case. Let's say that EX0 is 0 and EY0 is not. So we get EY0 and the locus is here, right? We can make a table, if this is our electric field, we can make a table, omega t, and what do we get for E? EY, right? We get, so when omega t is 0, assuming phi y is 0, right? Then it won't matter for the polarization, but let's assume that phi y is 0. Cosine of 0 is 1, so we get EY naught plus. Pi over 2, we get 0. 3 pi over 2, we get minus E naught y plus. And 2 pi, we get 0 again. So this is always in the y direction. So it starts out here at 0. It becomes E naught y plus at pi over 2 omega t. Then it goes back to 0. Then over here, this is at omega t equals to 3 pi divided by 2. Yeah? Okay, now, if we have, so this is linearly polarized in the y direction. If we have the case of both EX and EY, so we're not assuming that EX naught is plus is 0 or EY naught plus is 0. If we have both of them in general, we still observe at z equal to 0. Then we have an EX component and EY component. If we further assume for now that phi x and phi y are 0, then what we'll have is a straight line directed at all times along a line that makes an angle psi with the x-axis, right? We can find that angle by taking the inverse tangent of EY over EX. If you divide these two, the cosines drop out, and you get the ratio of the real amplitudes, EY over EX, EY naught plus over EX naught plus. And we could find the magnitude of that vector, basically going to polar form, right? By taking the square root of EX squared plus EY squared, and we get this expression here. So we can see as a function of time that this electric field will change its magnitude, right? I guess you don't want to call it magnitude in the real domain. Call it magnitude in the complex domain, but since it's in the real domain, call it amplitude. So the field is said to be linearly polarized in the side direction in this case. Those are easy cases, right? The linear polarization. But in all these cases, what are we doing? We're taking a plane wave which is traveling. We are looking at the plane wave at a, we're trying to look at the locus of the electric field as a function of time in a plane orthogonal to the direction of propagation. So we need to find the electric field as a function of time. So we can start to look at what that electric field vector looks like in time at different times. And we can then start to plot the tip of the electric field vector as a function of time at multiple times. We'll do that for circular polarization. It'll become much more clear. Okay, CP. So here we have circular polarization. So now we're going to do the same exact thing, right? We're going to look at the plane wave from behind it. So that's one other thing. When you, now that we're talking about circular polarization, let me see if I can think of an example. If I am a clock, right? 12 o'clock here, 6 o'clock down here. This vector to you guys is what? No, is it going clockwise or counterclockwise? Counterclockwise, right? But to me, from my side, it's going clockwise. All right. So look, how can we, so to you, this is going counterclockwise, right? But now let's look at it from my perspective. I'm going to rotate it still. So I'm going to start from this and go to my right shoulder. So to me, this is going clockwise. For you, it's going counterclockwise. Now I'm going to do the same thing. I'm going to rotate it toward my shoulder, right? Now you can see it's going clockwise, right? So what I'm saying there is that there's an ambiguity in defining whether this is a clockwise rotation or a counterclockwise rotation, depending on if the wave is coming toward you or if you're looking at it leaving away from you, right? So you have to break the ambiguity. And the way you do that is you define a convention where the wave is always, when you define the polarization, you always describe it in the plane of which the wave is traveling away from you. All right? So you're always behind the wave. So here, the wave is traveling in the z direction. So we're behind it. It's going into the board, right? And, okay, so the electric field from the last slide in general can have an x and a y component. If it's traveling in the z direction into the board, we're behind it. So we've chosen the right convention. And we have EX, EY, and Z going in, right? Here's the electric field. In general, has an EX and an EY component. We've plotted it in the real domain. And we're assuming that we're in the Z equal to 0 plane, so we can get rid of beta Z's. And now we're going to assume the case when EY naught and EX naught are equal in amplitude. We'll see that that matters. That's what defines circular polarization. That in a particular phase shift. EX naught equal to EY naught, we're going to call it E subscript R for E right. We'll see that there's a right-hand circular polarized plane wave. We're going to assume that phi X is equal to 0. And phi Y is minus pi over 2. So to tell you ahead of time, to get circular polarization, this is the electric field in general for all cases. To get circular polarization, EX naught has to equal to EY naught, and phi X and phi Y have to be different by 90 degrees. And we'll see exactly why that is. I don't know if I included that in this presentation. Let me check. Yes, here. Okay, I'm gonna jump ahead. So why does it have to be 90 degrees out of phase? Here I'm plotting EX in red and EY in blue, right? And then I'm adding the two together to get the actual E, right? EX is not the electric field, it's the X component of the electric field. EY is not the Y, is the electric field, is the Y component. You have to add them together to get the electric field. Now, if these two were in phase, meaning that E grew at the same rate as blue, so they started out at 0 together and they got to maximum and then came back, adding those together will give you a diagonal line, right? If you can imagine that. But if they are exactly 90 degrees out of phase, then this one is 0 and this is max, this one is max and that one is 0, right? That's what it means to be 90 degrees out of phase. Then when you add this to that, the addition of those two, the electric field rotates. Circular. The tip of the electric field is the tip of that black vector, and it traces out a circle, right? So to get perfect CP, you have to have 90 degrees phase difference between EX and EY. All right, so here we're assuming 90 degrees. It could be plus or minus 90, odd multiples of 90 to get right. But, okay, so, and then we have ER, right? So EX then is going to be E right, because they're both called E right. EX naught is equal to E right. Cosine of omega t, we assumed phi X is equal to 0, and we're looking at the Z equal to 0 plane, so it becomes E right cosine of omega t. Here we have EY, which is also E right, right? And then we're assuming that phi Y here is minus pi over 2, so we get cosine of omega t minus pi over 2 because we're looking at Z equal to 0 plane, yeah? So these are our two components. We can plot these up here. What happens? Let's make a quick table. So we have omega t, we have EX, we have EY. What happens at omega t equal to 0?
Yeah.
EX is?
Yeah.
ER, EY? 0, very good. Pi over 2? 0. E, right? 3 pi over 2? Minus ER, 0. 2 pi. Okay, so let's plot omega t equals to 0. E right, Ex is equal to E right, and Ey is 0. So here's the Ex axis, here's the Ey axis, right? So at omega t equals to 0, we have all Ex. The next one is pi over 2. At pi over 2, we have all Ey. So here's pi over 2. And at 3 pi over 2, we have negative. Here. Wait, we messed up. This should have been pi, yeah? Sorry, we're missing pi here. At pi, this is, okay. Well, okay. So at pi, this is the answer at pi, right? And this should be 3 pi. Oh my goodness, 3 pi over 2, yeah? Okay, so then here's 3 pi over 2. So you can plot it as a function of time, right? And the tip of this electric field vector, if you follow it, is making a circle. Furthermore, this vector is going in this direction with time, right? It started here, then it went to here, then it went to here. So it's traveling around the circle like this. Now, I'm going to jump ahead really quick to define if it's right or left circular polarized. You can either say that it's going clockwise and that's right-handed circular polarization, or use your hands. So a right hand, I put my thumb in the direction of propagation. If the vector is rotating, I rotate my fingers in the direction of rotation. If it's my right hand, so I start vertical, I go this way, right? That's RHCP because I use my right hand. Let's say it was rotating the other way. Then I would have to use my left hand, direct thumb in the direction of propagation. It's going that way, then it would be LHCP. We'll see that. We're going to do those examples. So remember, the electric field here is a CP plane wave. So it circulates like this. It's the plot you normally see, but really it's planes of electric field vectors. They don't change their magnitude, right? They don't go to 0 really. What they do is they rotate now, like that. Okay, so we'll come back. We'll study this a little bit more, but this is exactly what we did. Last slide, real quick. What we did here on, no, let me end here. We'll come back here. This is a good example to do. But basically, we do this plot that we just did on last slide with the table. All right. Okay, so good. All right, good. So yeah, you have to learn the language of these electromagnetic waves, right? You need to understand polarization, impedance, wave numbers, the loss, the alpha, the beta, and how to write these plane waves in oblique coordinate systems in order to solve problems and scattering and things. So this is you learning the language, right? Soon you'll be able to talk the language, and the polarization, we need to learn what that is so that we can solve more complex problems, right? This chapter is kind of a lot of definitions and things. The next chapter, we'll get to some interesting problems that you would face in engineering problems, and then we'll get to scattering and stuff, all right? So hang in there. All right, very good. See you guys next week. Oh, okay, very good. Let me, all right. This is your homework 3, good. Yeah, good. It's a good thing you got it done on time or in the original time. We'll give you 5 extra points on this. All right, so let me mark that. Let me mark it as +5.
These are the return homework?
Yeah, these are old. If you guys want to pick up, any homework you haven't yet, this is all homework 1 still, by the way. Homework 2 is coming. Next lecture, we'll have homework 2.
So if you have a lossy medium wave is that the same behavior as the evanescent wave?
Yeah. So an evanescent wave, it has the same. So if you look back at the table of the functions that we derived, evanescent wave is e to the minus alpha z, e to the plus j beta z, or minus j beta z.
So evanescent wave also has oscillation.
Okay, so evanescent wave does have oscillation, but in the direction of travel that, no, I'm sorry, it's not evanescent wave. It's a good catch, sorry, bad thing. Evanescent wave doesn't have oscillation. So it's just pure decay.
A real decay.
Yeah, it's cut off in that medium.
So it's just basically a combination of evanescent.
It's still a propagating plane wave in the lossy medium case, but it decays in amplitude.
Yeah.
In the evanescent case, it's not a propagating wave. An evanescent wave doesn't propagate. It just decays exponentially away from the interface.
Okay.
Yeah, no problem.
Professor.
Yes.
We talked about last Tuesday, we talked about some extra hours in the methods.
Yeah.
So I just consolidated all methods. I started reading the book this year, but it was Skype.
Oh, yeah, that's a good book, yeah.
It's a good book. So I just like consolidated all methods and asked.
Okay. Yeah,
If you can, then it's fine.
I think I might be meeting with the other student that wanted some extra help outside of the course. So maybe we can have you guys come together.
Okay.
I think I'm meeting her today. So why don't you come by to my office in like the next 10 minutes, 15 minutes, yeah?
Okay, all right. I don't have all my notes.
Okay, that's all right. Then you can come by anytime you want, different time you want.
Thank you very much.
No problem.
Have a good day.
All right, you too.